right, so I gave you this handout, and on the first page, it wants you to identify inspiration and exhalation on each of the 3 graphics. All right, so the first, oh, I got a pencil. Does that mean it's going to start drawing
It
things?
can, yeah. It's
Oh, great.
You have to hold it down.
I have to hold it down to draw?
correct, yeah.
All right, so look at the first graphic. What is it measuring? Pressure.
And time.
And which part is inspiration and which part is exhalation?
The line going up.
Inspiration is
The line
going
going
up.
up, and then line going down is inspiration.
All right, so going up, inspiration, and then coming back down, exhalation. All right. And on this one, what are we measuring?
Volume.
Volume. Air going into the lungs, inspiration. And then air coming back out, exhalation. Looks like there's a little bit of a volume loss here. It didn't go straight back to baseline. All right, on the third graph, what is it measuring? Flow. And above 0, what is this?
Inspiration.
Inspiration. And then what's down here? The valve opens, and then the air comes back out. Exhalation. So where does exhalation end and inspiration begin on this one? At 0, yes. All right, now what does it want you to know? Identify the peak airway pressure for each breath. All right, so look at your pressure time waveform and tell me what the amount of pressure that built up during the first breath. And it's going to be an estimate because we don't get exact numbers with the graphs. All right, about 23 centimeters of water. All right, what about the second one?
Second one is like 25.
Okay, centimeters of water. The third one?
About 30, 32, 33.
Okay, maybe like 31 centimeters of water. And then the last one?
34.
34 centimeters of water. Good. What is the pressure at the end of exhalation? So all the air came back out of the lungs. Did the pressure in the lungs go back to atmospheric pressure?
No.
Stayed at 5.
Right, so there's a positive pressure kept in the lungs at the end of exhalation, about 5 centimeters of water. And the volume of each breath?
Oh, 500, so
All right, like 475 ml. The second one?
like 490.
Okay, around 400 ml. The third one? 300 ml, and then the last one.
About 2.
Okay, 210, that's good. All right, very good. Identify inspiration and exhalation on each of the 3 graphics. I don't know if you have colored pencils or something with you, or if you just want to maybe draw the baseline really thick and then point to the top and label that inspiration, and then point to the bottom and label that exhalation. Got that labeled?
Yes.
Inspiration and exhalation? All right, and then for the next one, we've got pressure building up in the lungs. So peak inspiration would be right here. And then the pressure goes down because the volume is exiting the lungs. So maybe you want to draw a big dot right here and call that your inspiration or peak inspiration. And then maybe put an arrow and call this exhalation. Okay, what else does it want you to do? And then the inspiration and exhalation on the volume. Can you figure that when it's going up, that's the volume going in, and then when it goes back down, that's the volume coming back out? I guess you could put a dot somewhere there too. Like the tallest point would be the most amount of volume that went in, and then the volume coming back out again. If I draw on this, can I erase it? Let's see. What a mess. Okay. Can I erase it?
Top right.
Right click.
Oh, right there.
Right click didn't help.
I think that, oh no,
Oh, yeah.
there to change it to
The blue one.
the,
Yeah, the blue.
What's the blue?
no, that's the
Eraser.
hand.
That's the
Ah.
eraser. Yep. I think
You can
make the
reduce
dot
the size too.
Click on the black dot. You can make it, can't you make it smaller?
The one to the left of it, the squiggly line,
Yeah, the one to the left.
Yeah.
to the left of that, the dot. Then, yeah.
Left of the
Change
dot?
the line and figure the line thing.
Or do a
No.
line instead of a dot. Go up, that straight line,
No, the straight line tool.
squiggly.
Okay, this is an in-service on how to use ImageMate. Save it? Oh, great. I don't want to save it. Okay, I'm done playing. Let's keep going. The volume in, the volume out. So the steepest part is the maximum volume that went into the lungs, and then at that point, that's exhalation. So how much volume went into the lungs on this breath? 400 milliliters. Okay, good. All right, so this is showing you pressure volume loops where pressure is on the x-axis and volume is on the y-axis. And it's one breath of air. So when the breath of air goes in, this loop almost looks like it's laying down, doesn't it? And this one looks like it's standing up. So the reason for it appearing like that is the one that's laying down, you've got a lot of pressure building up when the breath of air is going in. So high pressure to get in just a little bit of volume. When you look at the graph on the bottom, you don't have much pressure building. But you've got a lot of volume going in. You see how it's tall? That means a lot of volume went in, but it didn't take much pressure to push the volume in.
So does it have to do with lung compliance?
Yes, very good. So what type of lung compliance would you expect to go along with the graph at the top? The
Stiff, very stiff, low compliance.
low compliance? And what about at the bottom?
High compliance.
High
That
compliance.
makes sense.
Easily ventilated, not much pressure, builds up. That's the one at the bottom. All right, so did you explain what causes the first loop to appear like it is lying down?
A lot of pressure building up.
A lot of pressure with very little volume. That's why it's narrow. Very little volume.
So would lungs be smaller?
The tidal volume would be
Instead of
smaller. Mhm. And then did you write the bottom one?
More volume and pressure.
Yes. So low pressure, high volume, an example of high lung compliance. All right, we're looking at the hysteresis curve again. Explain why the loop starts at 5 centimeters of water. So you see the letter A and it's pointing here. Why isn't it the breath starting at 0?
Because of
Because of
the,
heat.
Very good. So explain why the loop starts at 5 centimeters of water. There's PEEP set on the ventilator. The next thing, it says to write the peak inspiratory pressure. Okay, so you went to the furthest point, which is letter C, and then you went down, and you see it's about 30 to 35 centimeters of water. You got that finished? All right, next thing you have to do is label the side for inspiration. And then label the side for exhalation. Next thing it says is notice the lower inflection point does not exist. So I'll explain it to you right now, but you don't have to write it down because we'll go through it in detail in a little bit. When the lungs are empty, sometimes all the alveoli collapse, and when the next breath of air goes to fill up the lungs, before the volume can go in, a lot of pressure builds up just to try to get those alveoli to open back up again. And when you look at a hysteresis curve, you can see a lot of pressure, then all of a sudden air starts going in. So I'm going to show it to you on this lower curve. All right, so initially you see a lot of pressure going into the lungs, but not much volume. Then all of a sudden volume starts going in. So now the alveoli have opened up and now they can fill with volume. And so you'll see the volume going in. So I'll give that to you in the notes a little bit later. Okay, so moving on to the next one, it says notice the duck's beak. Can you see anything on this hysteresis curve that looks like a duck's beak?
Yes.
yeah,
Yeah, at the top. You see how this sticks out? So that duck's beak, it means that there's a lot of pressure building up when you're squeezing the last amount of air into the lungs. The last amount of air. What's a better word than the last amount of air?
The remaining.
The remaining tidal volume into the lungs.
a lot of pressure building up.
When the remaining tidal volume is going into the lungs. So a lot of pressure building up when the remaining tidal volume is going into the lungs. All right, you got that written down? All right, so what you see is during inspiration, the alveoli pop open, now the volume is going into the lungs, and after about, maybe around 500 mLs of volume that are in the lungs, to get the last 100 mLs into the lungs, it takes a lot of pressure to force that extra 100 mLs in there. And the reason for that is the tidal volume is too large for that patient's lungs. So the lungs are already full, and now you're saying, nope, we're going to put another 100 mLs in there. And when you try to squeeze more volume into the lungs than it can hold, it builds up a lot of pressure. And it gives you that duck's beak look. So when it asks you, what would you do to correct the problem?
Lower the tidal volume.
Yes, you would lower the tidal volume. That is what you were thinking?
Yeah, when I looked at it.
Very good. Yeah, if it's taking that much pressure to get that last 100 mLs in there,
You got it.
it's too much volume.
It's uncomfortable.
Yes, oh yeah. And it damages the lung parenchyma too. Notice for flow volume loops, notice that loops usually begin and end at the same point. This will only occur if the volume that was delivered to the lungs is the same volume that was exhaled from the lungs. And then it tells you, identify inspiration. Which part of this loop is inspiration?
Zero.
Everything above zero. Identify exhalation.
Anything below zero?
Yes, everything below zero. Okay, the next thing it wants you to do is compare the two flow volume loops. What causes the second flow volume loop to have expiratory flows close to the zero line during exhalation? Can you see the difference in the loops?
It's the recoil.
Yeah, so this one, when the air is exiting the lungs, it can exit pretty fast. Looks like 50 liters a minute on exhalation. But here, oh, it's saying 50 liters a minute initially, but then that really slows down and the flows are very, very small until all the air is back out of the lungs.
Very, very compact.
Yeah, these are obstructed airways. With airway obstruction, the patient tries to exhale and the airways close and the air can't get back out. So obstructed airways will cause a flow volume loop to look like this. Obstructed airways.
Oh, so then the tidal volume that was initially put in is still there. So
Well,
Is it all out?
it all came out because everything
It just
comes
took-
back to zero.
right.
It just took a
It
while.
just took on.
Yeah. All right, so the second one, you have obstructed airways, preventing the flow from leaving the lungs. And then on the ventilator, you can pull up airway graphics and look at your flow over time, pressure over time. When you're looking at something over time, when you're looking at a waveform over time, another word that's used is scalar, S-C-A-L-A-R. So this is a flow time scalar. So instead of hearing the word waveform, you'll hear the word scalar if it's showing you breaths over time. So breaths over time, it's called scalar, S-C-A-L-A-R. So this is a pressure time scalar, just showing the pressure building during inspiration and then exhalation. And then your loops, your flow volume loop, and your hysteresis curve. Okay, I think that was the last page, or is there more? Yeah, that was the last page.